Ami, just a moment, I will share my screen. Do you see my screen here?
Yes, I hear you, okay. And I can see your screen perfectly.
Okay, thank you. Good evening all. My name is Michael Zilberstein. I'm from Israel and I've been working with SQL Server since 6.5, since 2000. Last 7 years I'm an independent consultant specializing in performance and architecture. Started to work and present about column store indexes since SQL 2012 was in beta, I think. So today we'll talk about column store index internals, about the data structures behind it, the processing modes. So let's start. We'll start with wafers. What are wafers? You all know, probably like, but we'll talk about those wafers? No. We'll talk about wafers from the semiconductor industry. Those wafers are silicon plates which contain chips that should be tested in huge facilities, mostly in Far East, tested on machines. Each such machine costs millions of dollars. Each such plate contains from tens of thousands of chips. Different. Usually, each plate contains one kind of chip. For example, chip for Galaxy front camera, or chip for GPS navigator. For each such product, like chip for navigator or chip for camera, engineers build test program which contains sometimes tens of thousands of tests. In engineering facilities where chips are designed, it can be on even hundreds of thousands of tests. Tests of different type. Test can be burning unique ID on chip, or testing it under some particular electrical current or voltage or temperature or humidity conditions. Test results are usually numbers. In my demo, I use integers. In real life, they are usually decimal numbers with some precision. But there are types of tests that test results are strings. So here is the schema I will use for demo. Testers are those machines that we use for testing products. We have only 4 products. Wafers is the list of wafers we test. Each wafer is tested on one tester and belongs to a particular product. And we have 2 fact tables. The only difference between those tables is that in test results, in this one, I have built cluster column store index. The second table has primary key, which is clustered index. I will use it for comparison of performance and data sizes. Each table contains the same 50 million rows of data. So let's switch to Management Studio. Do you see the font is big enough? I hope. Okay. So
yes, it looks great.
Yes. Okay, thank you. Here are 4 products that we have. Galaxy S5 camera chip, S5 front camera chip, Sony Xperia camera chip. Those facilities usually test chips from different vendors. They don't belong to any particular company. Created 10 testers, just for reference. Wafers. In wafers, I've created 5 5,000 wafers, just a loop that creates 5,000 rows. Wafers are distributed equally among testers and products. So each product has 1,250 wafers. And here are our test results table. Wafer ID and chip ID is a key. When we work with the cluster Columnstore index, we don't have a key, we just have a cluster Columnstore index. 190 integer results columns and 10 text string results. All are nullable, but I don't use nulls here in my demo. I want to execute a population script. I executed it in advance. It took several hours to do so. Just another point, the second table, the one with the primary key is clustered index, I've created with the page compression. Here is the population script that creates 50 million of rows in each table. So let's just take a snapshot of how our data looks like. Wafer ID, chip ID, and random test results. And then we have strings. Another important thing, it's not quite random. We have only between 20 and 30, I don't remember the exact number of different strings here. It's important for when we will talk about when we speak about data compression. Okay, so we'll have two tables with the exactly same data, one with clustered index and one with primary clustered Columnstore index, and another one with clustered index with the page compression. So let's execute a query. The first one will be with on a table with clustered Columnstore index. I emptied the the buffer, so we are executing our queries on cold cache. Less than a second. Execution plan, parallel execution. I have 8 cores on my machine. Okay. Just a moment. The cluster Columnstore index scan with the predicate on wafer ID returns as expected quarter of the rows in the table because we have queried on a single product. So we have each product has quarter of a wafers. Each wafer has 10,000 units. That's another point I forgot to mention. For each wafer, I created 10,000 units. So took less than a second. Let's execute same query on clustered index. It runs. I can tell you that it will run about 20-21 seconds. If we look at the execution plan, create it in advance, just a moment, we can see that the plan, clustered index scan, plans for, clustered index scan, clustered index seek, sorry. The plan is pretty similar. Clustered index seek, the first part here is pretty neglectable because you know, we have 4 products, we have 5,000 wafers, so it's very lightweight. And here we have clustered index seek that returns 12.5 million rows. We have same thing with the clustered Columnstore index. So why it takes so much more time? 21 seconds exactly. You can see 21 seconds. So why does it take so much time? let's go back to PowerPoint and see. Sorry. Okay. Let's start with storage internals. The tables we are used to work. We all used to work on store data in rows. So each page, 8 kilobyte size, contains rows. In our case, we have probably, I don't know how many rows we have considering page compression. Without page compression, our row length is slightly more than 1 kilobyte, so we can have probably 7 rows in a page. Considering page compression, it can be a little bit more, but not too much. Contrary in a column store, the page, that data is still stored in pages, but each page contains data for single column. So page 1 contains data only from column 1, another page also from column 1, another page from column 2, and so on and so on. The pages are compressed automatically. You don't have to specify page or row compression. Actually, you can't. When you create clustered or non-clustered column store index, you can't use page or row compression. It is compressed automatically using other compression algorithms. We'll speak about it later. It uses some buzzword, vertipack or X-velocity compression, the same engine that is used in Power Pivot in Excel and in and now also in OLAP, tabular data model. That's the same compression engine, and it performs many of its operations in memory. But the important thing to remember is that the data is the pages contain only data for a single column. So, what's the difference? If we consider our query, clustered index seek on a table with clustered index should actually extract all rows, 12.5 million, but rows, meaning all 202 columns we have, 2 columns of the key, wafer ID and chip ID, and 200 tests column. While we actually need only only 2 columns. We need wafer ID and we need test 135. We can't index, we can't create covering index for each of the tests column. It's unrealistic. So so we have to query clustered index, and it means that we need 2 columns, we query 202 columns, so it's 100 times more data. We query 100 more times more data than we actually need. So one of the huge improvements or differences between column store index and the indexes of balanced tree index we have we are used to work with is that in column store we query only the columns which are actually required for a query. The second thing, columns are compressed, and considering that each column has a single data type, so it's much easier, and we achieve much higher compression rates when we compress data from the same data type. When we compress integer numbers, it's much easier than we have to compress integers with string, with dates, with probably binary data or unique identifiers. Compression ratio will be much higher. Of course, less I/O. In our case, it was 100 times less I/O. Better buffer cache hit ratio, of course, because when we query clustered index, we query all its columns. So all of them go to the memory. So actually, quarter of the table was uploaded to memory and took occupied space there when we query clustered the index. Contrary, when we query Columnstore index, only 2 of the columns occupied space in memory. So data in memory is much more relevant. Another huge improvement is new query execution technology. If you studied how execution plan is built, in the bottom line, it's always it's built from iterators, and between iterators, it's always the function that runs is get next row. You can see in the plan that 100 or 1 million rows go from iterator to iterator, but internally it's always get next row by agonizing row. The new execution mode, which works only with the Columnstore indexes, is batch mode, which works with which processes rows in batches or vectors, which consist about 1,000 rows per batch. It doesn't mean that you have only this work mode with the Columnstore index. You can also work row by row. Actually, one of the performance problems is one of the differences between queries with nearly same plan, which makes use of the Columnstore index, can be batch mode or row mode, and we'll talk about it later. And better parallelism, better algorithm. What does it mean, better parallelism? The core of Optimizer has been built and programmed in the years when a computer or server with 2 cores has been considered a strong piece of hardware. So now, when we work with pretty much the same algorithms, parallelism sometimes makes things even worse, or at least doesn't improve as much as it could. There are query types that benefit from parallelism. There are query types that don't benefit, and even sometimes there is intra-query parallelism deadlock. And actually, if you want to explore this topic, I've heard you can. There was a great presentation by Adam. I don't know how his second name is. How his name is spelled, Mashnik or Mahanik. Not in the last past summit, but the one before, he had a great presentation, great session on parallelism. So, usually we need this session because Adam explains which query types benefit from parallelism and which don't. Here, parallelism, parallel algorithms with Columnstore indexes has been designed starting from 2007, and they were designed specifically to make better use of multi-core machines. So here, scalability is nearly linear. If we double number of cores, the performance of queries with which use Columnstore indexes will almost will improve by twice or maybe a little bit less. Nearly linear scalability. And I've talked in the previous slide, new execution mode. Now you can see it in the query plan. Execution mode, batch, or can be row. But when you see in query plan execution mode row, it means that something is still wrong. You probably can improve your query performance by even an order of magnitude. How data is stored inside the index. Data is stored in segments. Not entire column can be stored in in a single page. So rows in a table is divided into segments. Each segment can contain between 100,000 and 1 million, a little bit more than 1 million, this exact number of rows. Who decides about how many rows will be in each segment? We'll talk about it. Each segment is compressed. Okay, so for example, I'm taking the segment, highlighted segment, about 1 million rows. Each page contains one column, but each page knows, we'll see the data dictionary, which segment it belongs to. You know, we still have to keep in memory that the query returns more than one column. So we have to know that some row from the first page is the same row than row from the second page, and we have probably 1 million rows here. So we have to connect between rows also. The storage is still in pages, 8 kilobyte pages like we are used to. SQL doesn't have other storage types, but it's stored in lob segments of particular type, not the one we used to for binaries. And segment for a single column is a unit of transfer from disk, meaning when we query even one row from a segment, one row and one column, entire column from the segment will be uploaded to memory. Okay, let's go back to execution plan now and see what we have here. First of all, clustered column store index, see the reads. It's I think about 16 or 18 times less. If we go to table IR, we will see that with the cluster column store index we have 1.4 million read-ahead reads. With the column store index we have only 100 slightly more than 100,000 reads. Same with CPU. We have batch mode, so we used 10 times less CPU. So both less reads and less CPU bring to the result that duration here with of the same query on cluster, the column store index is half a second, and here is 21.6 seconds. When I have seen this first time, I thought it's black magic, because what can be more efficient than you know, cluster index seek? Sequential I/O, the most the efficient thing that can be in SQL. So it appears that there are algorithms that are even more efficient and much more. Okay, let's go back to presentation. Okay. Batch, let's talk a little bit more about batch mode versus row mode. Not long ago, I received an email from my friend, a colleague, that asked me about some query that he has built a column store index on a table, and the query indeed makes use of this column store index, but in a plan it used row mode. Sorry, here. Execution mode was row, and considering that the query had to go over 11 million rows, it took pretty much time. So my friend thought it can be that it's probably because of statistics, but statistics were up to date, so probably something else. When I looked at his plan, I've spotted something interesting. Estimated and operator cost is 4.7. What does it mean? When the cost is 4.7 and you didn't modify instance level settings that come with the default installation, then the default setting for threshold for parallelism is 5. When estimated cost is below 5, optimizer doesn't consider parallel execution. And batch mode can work only with parallel execution. I don't know why people in Renmond designed it this way, why a single core can't query rows in thousands using batch mode, but that's how it works. So the minute I've seen this point, I've sent an answer recommending to try and force parallel execution. There are two interesting things with the query trace on hint. First of all, that's new in SQL 2012. You can force a trace flag on a single query level. And the second, the flag itself. This flag forces parallel execution. I don't know, frankly, whether it is documented or not, but you can find the usage of this flag in a blog of Paul White about query execution. He uses it mainly for demo purposes, but since you can enforce flag on a single query level, it's much more safe for usage. You don't enforce it on an instance level or even on session level. It's just for a particular query which you know whether can benefit or can't benefit from parallel execution. So the answer was amazing. The query ran very fast with the flag, less than a second. Actually, I didn't see many forums or books online articles about it, so just take into account row mode sometimes is just because estimated query cost. Take it into account. Now let's look at the data dictionary. We have two dynamic management views. One, this Columnstore segment contains a row for each column in each segment. Another one, Columnstore dictionaries, contains a row for each dictionary. What is dictionary? Later. Let's just take a look at how dynamic management views look like. The most important thing is in the first this Columnstore segment is min data ID and max data ID. Columnstore index is very much is not similar to the indexes we are used to work with. I mean balance tree, B-tree indexes. They don't keep data in a tree-like structure. The structure is segments, but for each segment, when it is built, we know row count and we know data boundaries, min data ID and max data ID. So segment elimination or query that uses this index, Columnstore index, goes to the sys Columnstore segments. And for example, in our query, we are filtered by wafer IDs. If you remember, wafer ID that belong to a particular product. So it goes to this dynamic management view and takes a look. This is data ID. This is not the actual value. Column 81 is wafer ID, but it's not the it's probably data, but it's probably data ID because of the dictionary. We'll talk about it later. Dictionary, but what is important to know is dictionary can create its own IDs, and data is kept with dictionary IDs and not the actual wafer IDs or chip IDs or test result IDs. So that's the way query optimizer uses this index. When query flow comes to this index with 1,200 wafers, first of all we check which segments can contain these wafers, and only when we find the relevant segment, then data is the segment itself is queried from disk in order to find the relevant rows. Dictionaries, that's a small view. It's column ID. Not every column receives dictionary. In our case, only first two columns, 1, 2, which are wafer ID, chip ID, and the last 10 columns, which are textual, string test results, if you remember. What we can, another thing that we can extract from dynamic management view is size. I will send my scripts to Ami later, so you will be able to take it or download it from PAS site. For example, this is in the size of all clustered Columnstore indexes in the database. This is the segment size. This is dictionary size. Here, since we have dictionary, we have to consider it too. We can take measure size per index. So this is table name, index name. This is table we've been working with so far. 2 megabyte of data dictionary and 18 gigabyte of data. We can measure size per table, which will be same as previous because we have one index in each table, and we can measure size per column. For every column, we can see the particular, since data pages have only single column, contain only a single column, then we can measure size per column. So we can see that numeric integer test columns are all have the same data volume, about 95 megabytes, and the textual are also 0.1 megabyte. Actually, I would have expected more because if you remember, strings are pretty. Just a moment. How data looks like. We have pretty long strings there, 30 characters. So that's the way compression works, and why it works this way we'll talk in a minute. Just another small point. In Columnstore dictionaries, we have type. Here, type is 1. Column 1 is wafer ID. Type 1 is hash dictionary containing integer values. Type 3 is hash dictionary containing string values, which makes sense. Column 193 is one of the string test results columns. So, just for the sake of completeness of this presentation, I believe everybody can read books online, but just for completeness, I've added screenshots from books online. Limitations. Cannot have more than 1,024 columns. The important cannot be created using include keywords. if you think about how the index is built, it's actually all columns are included. It's not sorted. So cannot include ascending or descending. The most important limitations are features, which column store index cannot be made use in combination with. Replication, for example. You can't replicate in the table which has a column store index, no matter clustered or non-clustered. So that's a huge limitation. File stream, change tracking, data capture. And you can't create a clustered column store index on a table which has any one of the following data types, columns of the following data types. In SQL Server 2012, it was only unique identifier. In SQL 2014, unique identifier is supported. You can create non-clustered column store index if a table contains columns of this type, of any of these types, but your index just can't contain those columns. Take into account that when you create clustered column store index, it automatically contains all columns in the table, of course. Okay, now let's go a little bit deeper into data compression. How we achieve such a compression level. By the way, we didn't compare our tables. Let's do it. We have this one. And we have this one. A table with clustered column store index is 19 giga. Table with clustered index and page compression, 44.6 giga. 2.5 times more, and it's considering page compression. Without page compression, it would be even more. So, how do we achieve this? There are 4 encoding algorithms. Dictionary encoding, run length encoding, also known as RLE, by first letters, Huffman encoding, and Lempel-Welch encoding. Also in SQL 2014, in the latest version, another mode, Columnstore archive, has been added. It's compression algorithm similar to gzip. We'll speak in details about first 2. Last 2 are more complicated. There are great Wikipedia articles about both of them. Anybody who is interested in math and is welcome to read it. I've read it with great interest. So, encoding versus compression. The very important thing to understand is what is encoding and what is compression. Those 4 algorithms are encoding. A Columnstore archive is compression. And what is the difference? Encoding is a process of transforming information from one format into another. It's like what does it? What I mean? I substitute. For example, one of the last 2 algorithms that we want to talk about it in detail. Just substitute the strings, frequent strings, with something smaller. For example, some article on socioeconomic stuff probably makes use of many terms like socialism, capitalism. So we have many ISM strings. So probably it will find it useful to substitute ISM with 1, for example. So we have 3 times less length here. But what it means is that when I read the encoded string, I can start to decode it initially. I don't have to decode the entire document. Unlike zip or compression algorithm, that when I compress file, I have to uncompress it all before I start to read it. So encoding It's just the process of transforming information from one format into another, which then this another format just takes less space. That's it. But we can process encoded data without decoding it first. You don't have to decompress the entire page. If you have a page that contains 1 million rows or 100,000 rows, we can look at the first row or second row without having to decompress or decode the entire page. Compression, on the contrary, is must be decompressed. That's like zip. And that's the difference between the usual encoding and Columnstore archive, which uses similar to gzip algorithm. Okay, now dictionary encoding, the first one. Dictionary encoding, let's take example with the test 199 column. It's a string test results. We have only 26 distinct values here. Each value is about 30 bytes, 30 characters. So internal dictionary is built on the fly, which substitute those lengthy strings with numbers, IDs. 1, 7, we have 1 to 26. So 1 to 26, it's enough. 5 bits are enough to represent any number from 1 to 26. So instead of 30 bytes, we have only 5 bits per row. That's why our string results segments occupied less space than integer results. Run length encoding. Run length encoding is very simple. If we remember, we have created 10,000 rows per wafer. For each wafer, we have 10,000 chips. So, if after a build or somehow all those 10,000 rows are in the same segment, then the encoding is very simple. Here we have rows 1 to 10,000 with wafer ID 107, for example. Rows from 10,001 to 20,000 with wafer ID 108. So RLE algorithm just said that from first row to row 10,000 we have the value 107. From this from row 10,001 to 20,000 we have 108. So this way we can keep million rows in single page. This algorithm also hints or we should consider how do we load data into a table. If we used to filter data by wafer ID, for example, then it's our interest that a single segment will contain as few distinct wafer ID values as possible, so that when we come to data dictionary to segments dynamic management view, we can make an effective use of min data and max data per segment and eliminate as many segments as we can. If, on the contrary, we load data in the way that we have a million different wafers in each segment, then query by wafers will have to actually go to disk and query much more segments. This is the very important consideration on loading data. When you load data, consider how you query it and adjust loading so that querying will be more effective. How data actually looks like. There is a new undocumented column, but it's undocumented the same way as DBCC page has been and still is undocumented. It's called DBCC CS Columnstore index, and it is actually DBCC page for Columnstore indexes. Those are parameters it receives: the database name or database ID, row set ID, which is Hobbit or partition ID from Columnstore segments, column ID, row group ID, which is segment ID from sys Columnstore segments, object type, 1 for segment, 2 for dictionary, and the print option like the last parameter we've seen in the DBCC page. Here is how DBCC says index output looks like. The interesting things we can find here are RLE, so we know that this particular page is compressed using RLE algorithms. We can see how many lob type, that's the new lob type where this data is stored. We can see that value 15 count 38,400 rows, 38,400 rows. So for a single value, we have, if we go to Management Studio Query, we can see that this single page encodes as much as 1 million rows, single page. We can't even dream of it with the traditional indexes. So let's go to Management Studio and see how it is, how it looks like. I'm querying column 195, which is a textual result for segment 13. So 1 million rows, same. But we have several data sets in this page. We have this one. We have another one with position. Position, or it's a sort of offset array. And some bitpack data header. Bitpack algorithm and so on. By the way, we have min data ID and max data ID, same as we have in Columnstore segment dynamic management view. Okay. Columnstore archive. In SQL Server 2014, Microsoft added additional compression option called Columnstore archive. Now when we create a Columnstore index, we can specify the default compression option is Columnstore, but we can specify that the compression is Columnstore archive. It adds about 30% additional compression, but since it's compression and not encoding, and I want to emphasize it's compression and not encoding, when you query it, it takes more time, and there is of course CPU penalty for unzipping or uncompressing the data. So make use of it on historical data that you don't access frequently. By the way, here it's the Columnstore archive or Columnstore compression can be specified on partition, on table or partition level. In other Columnstore database vendors, particularly Vertica by HP, enable us to specify it on a column level. So, for example, if I have I know that textual test results data is seldomly accessed, much more seldomly than integer test results, so I would like to compress it probably, or to compress it more than it's compressed now. But in SQL Server I can do it. I can specify Columnstore archive only on table or partition level. Let's see how we do it. Yeah, I've created have created 2 more tables, same structure, test results CCI small and CCI test results CCI small archive. Why small? Because I inserted data only for for 100 wafers there. We have 5,000. I added only 100. Means 1 million rows, I think. 100 multiplied by 10,000 units per wafer. Yeah, 1 million rows instead of 50 million. So I've created in advance because it takes time. Let's compare. Test results, small, which is Columnstore, normal Columnstore. Segment size is 363 megabytes. Columnstore archive is 333 megabytes. It's not linear and depends on your data. It can be 30%, it can be less, it can be sometimes more. Depends on how your data is compressed. Let's execute those two same query that we have tried on Columnstore versus clustered index. Let's try it on these two tables. I've executed it in advance, and here are results. Plan is, of course, the same. What you can see is, just a moment, this is small and this is small archive. Small archive, the estimated cost is less, but see, CPU is more on the small archive. It's quite logical. It has to, there is additional penalty of uncompressing data. But reads are less because data is compressed, so we have less data on disk, less pages on disk to query. Duration, it's in this case querying archive took more time because of the CPU. So due to the penalty of uncompressing data, take into account that Columnstore archive query on partitions or tables with which are archived using Columnstore archive compression will take longer. Okay. Resource consumption. Creating Columnstore index is very resource consuming operation. On another hand, no, it's Columnstore index can be created on enterprise edition. So it's enterprise feature, and your servers are in accordance with it. Usually they are strong and contain much memory. My laptop has 8 cores and 24 gigabytes of memory. I guess with much stronger server, creation of index could take less than hours it took on my machine. Although all the numbers in this slide are approximate, and they can vary depending on degree of parallelism, number of columns, number of string columns, and other factors. But what you can be sure that creating Columnstore index takes longer than creating a binary tree index. It's pretty clear and requires more resources. Approximately, just take it as a rule of thumb, memory required for creating Columnstore index is 4.2 multiplied by number of columns in Columnstore index plus 68 multiplied by degree of parallelism and plus number of string columns multiplied by 34. That's the rule of thumb. In any particular case, it will be different, this way or that way. You can use it as an approximation. Another thing to consider, CPU consumption, of course, depends on degree of parallelism, but if table contains less than 1 million rows, Columnstore index will be created using single thread. On the other hand, I am not sure you will bother creating Columnstore index on a table with less than 1 million rows. Okay, let's compare index types. clustered, non-clustered, Columnstore cluster, and Columnstore non-clustered. Data representation. Clustered index, same as Columnstore clustered index, is a table itself. It's physical data representation. Non-clustered, same as Columnstore non-clustered, is a separate data structure aside clustered index or heap. So when you estimate space consumption, just take it into account. Sort order. Cluster index is a physically, so it's like a phone book, or it's a physical sort order of data. Non-clustered index is sorted by index order. Columnstore indexes are unsorted. You can look at them as if all columns in Columnstore indexes are included columns. You don't have index column, all the columns are included. Additional indexes, when you work with clustered index, you can have, say, one cluster or 0, and you can have as many non-clustered indexes. When you have non-clustered indexes, of course, additional indexes are allowed. When you're on clustered Columnstore indexes, you can't create non-clustered index. And that's a big gotcha, or big thing you should consider. That's how you work with your table. If you work with in big batches, that's then Columnstore cluster index fits you. If part of the workload exists or insert delete of a single row, especially when you use exists or queries, when you query single rows, since you can't create Columnstore, you can't create balanced tree indexes on a column with clustered Columnstore indexes, you should consider it heavily. Probably clustered Columnstore indexes won't fit you in this case, and you would like to work with non-clustered Columnstore index and be able to create balanced tree indexes. Of course, the limitation of non-clustered Columnstore index is that it makes the table read-only, so that you can only work with partition switching. You can't insert data or bulk insert data into the table with non-clustered Columnstore indexes. It was a limitation in SQL 2012. It remains so in SQL 2014. Okay, another slide, also for the sake of completeness, and for those of you who
Michael, we have
yes.
about 1 minute till we must finish, so I suggest this is a good time to wrap up.
So I thought it was an hour and a half.
No, it is 1 hour, sorry.
Okay. The SQL 2012 limitations are they're due to the fact that development teams in Redmond didn't have enough time to implement all the algorithms, so outer joins, not in, scalar aggregated, multiple distincts in a query, didn't work with batch mode, worked with the row mode. For all those cases, you can find in books online on TechNet efficient rewrite options. How can you rewrite your query and still make use of batch mode? Okay, then I will omit loading data part and go to the end. And with the last slide will be industry overview. We have other vendors besides the Microsoft who provide the Columnstore column-oriented databases. This is a screenshot of Wikipedia. There are two considerations that you know. Scaling type. SQL works on a single server. There are other, same as Sybase IQ, for example. Other vendors like Vertica, Exasol, or Paraxel work with on scale on nodes. You can add nodes. There are other vendors which supply appliance. Teradata, probably the oldest one. Another thing to consider is pricing model. Appliance is appliance, you know, Teradata, for example. SQL charges per core. Vertica, Paraxel, Exasol charge per data size. They measure raw data that you load into your tables, and bill for data. Those are two considerations that you should know when you consider which solution to choose for a column-oriented database management system. So references and questions. Thank you. I thought it was 1 hour and a half, so probably another session will be useful for data loading.
Yeah, maybe we can make a whole session just out of data loading into Columnstore indexes.
Yes.
That probably can be enough.
Yes.
Yeah.
That's topic for a full 1 hour session. Yes.
In its own right. Okay, thank you very much, Michael. It's been a pleasure. I hope you all enjoyed this session as much as I did, and I've learned a lot today. And I hope to see you again in our next session, which will be is currently planned for June 3rd. But watch out for the news. You'll get emails, and whoever registers for our website, IMVC, in-memory virtual chapter, .sqlpass.org. We'll send emails with the invitations. Watch out the social media channels, etc. We'll announce the content and the schedule. So thank you very much, and hope you have a wonderful day.
Yeah.
Thank you again, Michael.
Thank you. I will send you a presentation. Probably I will remove data loading part from it. So
okay, yes, and I will upload it to our virtual chapters homepage so everybody can download and play with it himself. So with that, I conclude today's session. Have a wonderful day.